Okay, before we explain our topic for this project, we're going to discuss two problems that we're going to solve related to mobility. The first one is corded power tools. It's really difficult to use a tool with a long cord getting tangled up and dragging behind you. Problem number two is expensive e-bike batteries, and the ones you can't afford don't have much range. Our solution to both of these problems is to develop a mobile power supply, one that can deliver both AC for tools and DC for e-bikes, scooters, whatever. The battery will be able to either replace or supplement your battery for your e-bike, and then you can also use it for your AC powered tools such as leaf blowers or saws. Here's some numbers we're going to aim at for the ratings. 120 volts RMS for the AC at 60 hertz, and then we're going to aim at 48 volts for the e-bike supply. Okay, so let's explain how to build this, starting with the AC section. So far we got just a battery and an AC output that's required. So how do we do that? We could start with an H-bridge controller, which takes a DC voltage and converts it into an AC signal with the load connected at those middle terminals. To get the AC voltage, we alternate the switches in diagonal pairs, and that's how we get different polarities across the load. And if we change the time the switches are on, that can translate into a different voltage level. So going back and forth, we can see how we get those polarities. The output across the load is going to look like this, some sort of a square wave. This is an SPWM signal, which means it's a pulse width modulated signal related to a sine wave. To control the switches in the manner we described, we need a SPWM controller, which feeds in two different signals to each diagonal pair, controls them in such a way to get our SPWM signal. We finally feed that into our output filter, then we have our AC signal. Now that we have the AC signal, we need to get it to the value. We need to get that signal to the level that we desire. 120 volts RMS. So we have two options. We could throw a transformer at the output and boost that 60 hertz signal, or we can put the boost before the H-bridge and use whatever frequency we want, probably a higher frequency before the H-bridge. Turns out we're going with option 2 just because if we boost it at a higher frequency, we require a smaller transformer, and since this needs to be a compacted design, we're going to go with the smaller transformer option. To go from 40 volts to 400 volts supply for the H-bridge, we're going to be using this circuit. It's called a push-pull converter. It uses two switches to alternate the current on the primary side of a transformer to create an AC signal on the secondary side. At our 400, it's going to be 400 volts peak. And this is the function of it. So one switch turns on, battery input still goes in the same direction, but the current changes direction on each cycle. All right. So just like the H-bridge, we need a controller for all this. It gets fed into the power section, which is the push-pull converter. We have some sort of a square wave, which we rectify filter. That gives us our DC voltage. And altogether, we have our control for both sections, we have our power and our filtering sections. And then finally, we feed our DC from the push-pull into the H-bridge. Okay, onto the e-bike power. We have three options. We can do boost, buck, or buck boost. Right now we're aiming for a boost design because we're starting with 42 going to 48. So we can do boost or buck boost. The only issue is that each of these designs will not work as shown for a high current. The first way to think about this is to put a bunch of them in parallel, but that's not entirely accurate. Simply doing this with the same PWM signal all fed into the same output won't work alone. The proper way to do this is with a master controller, a master power section, then copying that to a slave controller, and then having that slave controller repeated a bunch of times until you have your desired output current. Each of these slave controllers and the master controller will have its own feedback and be able to control its output pretty accurately. Here's the whole DC section together with the master controller, power section, all fed together to get the final output. Now the full system, we're going to be controlling both of these with an Arduino to have some sort of a mode select. We have a low voltage power supply to supply all of our ICs, and then finally a battery going to the push-pull converter and the master controller of the DC section. Here's the schematic for just the AC section and the schematic for just the DC. You have the master controller on the top and then the phase expander on the bottom there.
All right, so the circuit design details and results. So we got our part one, which is our DC to AC conversion. H-bridge and its components. So we had to decide between 4 NMOSs or 2 PMOSs on the high side and 2 NMOSs on the low side. We chose 4 NMOSs because they have better performance, lower cost, higher efficiency, less power dissipation, better swing and superior switching speeds when we compare it to PMOS. How's that going to work? The high side NMOS sources, they're tied to the high side of the load. So eventually, at the beginning, the NMOS is going to conduct, but once VS rises high enough, it's going to become larger than VG and the NMOS is going to turn off. Now we need a bootstrap. So what is a bootstrap? It's basically circuitry around a driver IC that's going to allow for a capacitor, high voltage capacitor to charge when the low side MOSFET's on, and then discharge between VG and VS when the high side MOSFET is on, which ensures that we always keep a VGS of 12 volts. All right, so do we just connect the gate drivers directly to the gates? I mean, we can, but it's going to be a bad inverter. So the gate driver circuitry. We got a Schottky diode to protect against inductive kickback during MOSFET turnoff that leads to voltage spikes that can damage our components. We've got a gate resistor that's going to increase turn on and off time to decrease power dissipation, EMI, and protect against voltage spikes. And finally, our capacitor and resistor combo. The capacitor is going to protect against MOSFET self-turn on due to the Miller capacitance, and the resistor is going to be a discharge path for that capacitor so it doesn't retain a charge. All right, so now we did an FFT, and we had to see where the dominant harmonics were at that output. Turns out our dominant harmonics were above 500 hertz, I'll show in a sec. So we designed an LC filter for 480 hertz and split the L between both sides of the inverter output so that it would be a balanced approach. Here's our FFT before filtering. Here's our FFT after. It's beautiful, isn't it? All right, so now how do we control that MOSFET switching of the H-bridge? So we used SPWM, which compares feedback sine wave reference to a triangle carrier of 23.4 kilohertz to adjust the width of the output pulses and make sure that 120 volts RMS output is maintained. We chose unipolar switching because unipolar has less harmonics and less switching stress. So now we had to find out our requirements for the SPWM chip. It needs to be capable of unipolar, take a scaled down feedback from the output, have gate drivers with built-in bootstrapping, and most importantly, have dead time insertion to prevent shoot through. Because essentially, if you have all 4 of your NMOSs on at the same time, they'll pretty much short. So you need to make sure you have PWM signals that have no overlap between their on times. And that's exactly what this shows here. All right, now we have to figure out our input voltage required to get 120 volts RMS output. So we had to tune our modulation index by simulating the SPWM chip in LT Spice and adjusting that ratio of reference to carrier to see when our cleanest output happened. Final modulation index, which was 0.425, which resulted in input voltage required of 400 volts. We couldn't have an M too close to 1 because we'd have high harmonics. We couldn't have an M far below 1 because we'd have low efficiency, and M greater than 1 resulted in overmodulation. So that perfect 0.425 was our decided value. Now, how do we make that 400 volts DC? We'll talk about that in the push-pull converter design. All right, so now we just need gate drivers. So all that really matters here is the bootstrapping. The rest is not so important. So as we can see, in order to have a bootstrap circuit actually work, VG needs to be 412 volts to keep VGS of 12 volts. All right, here's our full circuit all together. Now, the H-bridge and associated switching requirements are designed. What about that 400 volt supply? Let's go to the ideal component store and buy one.
Okay, so to design the push-pull converter, well, okay, you know what? First, we'll explain the various components in the push-pull converter. First, we got the PWM controller, our switching MOSFETs and transformer, the rectifier and output filter, feedback network with the opto isolator, some input protection, and then a voltage regulator for the PWM controller. All right, so to design the transformer for this, we had to go to various data sheets, look at a bunch of curves, much like this. And first step is to pick the material. We want a material that has a high saturation flux density and a large predictable linear region. That gives us a good area to work in, and essentially we're going to be designing to work just in that linear region. Once we have our material selected, we're going to be trying to optimize all of these parameters to make our transformer as small as possible. To help visualize the balance between all of these parameters, we have these series of plots. So first, we are plotting the magnetic flux density on the y-axis versus the number of primary turns on the x-axis. Each trace represents a different core size, and each plot represents the test at a different frequency. So once we have all that labeled, we can set a marker at 5,000 Gauss, which is the limit for our linear region. And then we can simply just pick all of our options that fall below that 5,000 Gauss mark. So you can see we have nothing at 1 kilohertz and more options as we increase the frequency. We can select a couple, for example, and then move on to designing the windings. So for a high current on the primary side, your American wire gauge is always going to be larger than the maximum skin depth, which is a problem because if your wire diameter is larger than the skin depth, you're going to have a bunch of thermal losses because the current is only going to travel through the edges. The solution to that problem is Litz wire. So simply you just bundle a bunch of conductors that don't exceed whose individual diameter don't exceed twice the skin depth. Then that should help mitigate your losses. The problem with the Litz wire is that it's pretty large, and wrapping that around a small cord to begin with is pretty difficult. But the solution to that problem is to parallel a bunch of transformers, which would work because it lowers the current on each primary side, and it also it requires a smaller individual transformer as well. So we couldn't do that because adding an extra parallel transformer added too much design complexity, so we decided to design this for a larger transformer to just make it work. So modeling the transformer, we use the Chan model here to simulate the flux density, and this is how it looks in LT-SPICE. We got some instruction on how to use the Chan model on the EEV blog, but simply to use it, all we had to do is plug in some parameters from our transformer core that we chose. This is an example of some of the physical dimensions, but it also requires a couple of the magnetic properties as well, such as the magnetic flux the maximum saturation flux density, as well as the remnant flux density.
All right, so here's our simulation results in LT-SPICE. This is the output of our AC section. So as you see, we have 120 volt RMS sine wave as we expected. And this is just to show SPWM frequency in relation to our actual sine wave frequency. So hardware implementation. For the implementation, we ended up just using a 12 volt, 400 volt transformer board rated for 500 watts, just to implement a proof of concept for the H-bridge, and then use the rectifier design. The rest remained the same. So first we tested the inverter without the push-pull, which in hindsight was a great idea. So without the push-pull, then we tested it with the push-pull. So our results are just showing the SPWM with dead time. First, we wanted to just make sure the controller itself worked with proper dead time before we plugged it into an inverter at that high of a voltage, because that would be dangerous. So here's the testing the inverter before the push-pull. We got a 450 volt DC input, gave us 114 volt clean peak-to-peak sine wave, and then 100 volt DC input gave us a not the cleanest, but still pretty decent 225 volt peak-to-peak sine wave output. We expected that because we actually designed it for 400 volts, we weren't going to get it to be super beautiful, plus the way we were probing without differential probes, and with using the math function made this a little more difficult. All right, so testing the inverter with 230 volt push-pull first before we changed that transformer wire to the 400 volts. A shocking turn of events, not really. The initial voltage spike that happened from the transformer blew our MOSFETs and our controller. So that happened and we didn't have time to retest it, so it is what it is. So part 2, the DC to DC boost converter. So here we have, as we mentioned, we needed a multi-phase approach, so we have a multi-phase expander boost converter chip. Basically, that is multiple phases that are controlled by a boost converter controller that controls all the switching signals and distributes them across multiple phases of that converter, so it's essentially 4 boosts in parallel. All right, so here's we needed calculations and tuning for basically every value at every pin, but these are the important ones. So we had an output voltage resistive divider, R sense for the current sense amplifier, and soft start capacitance, a switching frequency of 25 kilohertz, and then we needed output capacitances and inductances for current ripple. Here's our simulation results. As expected, we had our 48 volts, which is what matters for an e-bike. 42 amps is fine. 40 amps, 42 amps doesn't really make a difference when you're dealing with e-bikes because their controllers decide the current.
Okay.